Okay, so in the previous sessions, we've been laying down the foundations for electronics. We've been talking about basic electronic concepts, right? And all that properties of materials, things like resistivity, conductivity. Okay, so if you recall yesterday, I said that the things that we are talking about are the reasons why electronics work as it does. Is that okay? So, how do all the things we talked about yesterday help us in electronics? How do we apply them? Okay, so in this particular, in what we're going to do right now, we're going to look at some of the applications of everything that we've talked about. Is that okay? Yes. So we're going to talk about basic electronic components. Okay, and again, I'm going to do a lumped approach, meaning that I'm not going to focus much on the I'm not going to focus much on the, what do you call it? My attention or my focus will not be on the details, okay? But I want to give you enough information so that you would understand and be able to build electronics intuitively, okay? That's the plan for what I want to do, okay? So that is what I mean by a lumped approach, okay? All right, so let's get started. Now, in all the previous sessions, yes, so we talked about things like conductors, energy sources, insulators. I mean, a lot, right? You remember all these things, I hope, okay? And we also talked about how their the fundamental behavior of electrical energy when interacting with matter. Okay, so basically the way electrons move, the way an electric field develops and all that, these are evidence of electric energy reacting with matter. Is that okay? Now, some of these things that we talked about are actually things that are in quotes undesirable, right? They are things like resistance, right? Because of resistance, we have to be charging our phone batteries and all that. Because we lose energy, systems lose energy. We are unable to efficiently move energy from one point to another. Okay, because of resistance. Short circuits. When a short circuit happens in your system, if you don't take care, you can damage your circuit, right? So some of these things are not actually desirable. Is that okay? However, if we are able to control them, we can engineer them into useful endeavors. Okay, we can actually use them for very important stuff, and that is what we are mostly doing in electronics. Okay, so we look at how nature behaves and try to see how we can beat nature. Is that okay? Basically, that's engineering. Nature behaves some way, and you see, the behavior of nature is predictable and consistent. Nature will always behave the same way. Water will always move from uphill to downhill. If you get to any place and you realize that water is moving uphill, then something is wrong. Okay, so we know that so far as water is concerned, it will always move from uphill to downhill. We know that if we throw something up, it will always fall back. Okay, so nature is consistent in the way it behaves, and that is actually what makes engineering possible. Now, imagine nature was inconsistent. Today, water can flow downhill, tomorrow, it flows uphill, the next day, it flows sideways. Then it would actually be very difficult to build electronic systems, right? Because it will be difficult building a system and tying it to a particular thing, because that condition would keep changing and changing and changing. Is that okay? But because of the fact that nature is consistent, we are able to capitalize on that to build electronic systems. Okay, great. So we know that definitely anytime that we mistakenly connect a path with the least resistance to electric energy source, there is going to be short circuit. If you do this in Ghana, the same thing will happen. If you do that in Nigeria, the same thing will happen. If you do that in India, the same thing is going to happen. Okay, so nature is consistent. In fact, if I do it today, the same thing, next year the same thing will happen. Is that okay? So that is the assurance that we have as engineers, that whatever we create, for the principles, they are not going to change. Okay, great. So we know though resistance is not a very good thing to encounter in circuits, but then we are also able to use resistance, the concept of resistance, and also the fact that capacitance, as we just talked about, to do useful things, right? Now, capacitance, because of capacitance, as we'll probably see tomorrow, because of capacitance, signals, when we are transmitting energy, this energy can receive some amount of delay, okay? Some amount of delay. And these are all things that we are not technically ideal, right? However, when, like I said, when we are able to control these events or properties, we can actually use them for very important or useful applications. Is that okay? For instance, using the idea that capacitance can actually cause delays in circuit means that we can actually create timing signals, right? We can create systems that can be engineered to release energy at some particular times or not. Is that okay? Now, there are also instances where we specifically need a certain amount of energy to move through a system. Is that okay? For instance, assuming I have a battery that is rated 9 volts, right? And I have a lamp that is rated 6 volts. From what we've learned, if we should connect this thing directly, the bulb would burn because the energy coming from the battery is more than the bulb can handle. Is that okay? So this is a situation where we would wish there is a way we can reduce how much energy would flow. Is that okay? And well, fortunately, that is something that we can actually do. Is that okay? So let's look at this analogy. I have this analogy that I do with what viruses, right? So remember when COVID came, the world was crying and searching for an antidote, right? A solution to COVID. And COVID is a virus. Usually the way you treat virus is by using vaccines, right? So how do vaccines work? Vaccines actually introduce a certain controllable and weak form of the COVID virus into your body, so that your body's defensive mechanism will learn how to deal with that particular virus and overcome it. Because most of the time we don't have drugs or those kind of stuff, antidote for viral diseases, right? We make the body fight. We give the body the ability to fight that disease on its own, right? Now, before the body can actually do that, we have to introduce a controlled amount of that particular virus into the body, and that's what vaccines do, right? So if you took the COVID vaccine, you technically deliberately introduce COVID into your system, so that your body now learns to build immunity against this virus. Is that okay? So basically, this is something that you can call a necessary evil. You are trying to prevent COVID by learning how to deal with COVID. Okay, so you introduce COVID to learn how to deal with it. Okay, so it's some form of a necessary evil, right? So although we don't like the effect of resistance in circuit, take note that those effects are things that we don't have control, right? But if we can actually find a way to introduce some amount of resistance that we want, then we can actually use that property to our advantage. Is that okay? So there is a way we could actually harness the property of resistance to do things in our circuit. Is that okay? Now, in the realm of engineering, we mold these characteristics, behavior, or phenomena into controllable units, okay? Each with specific values or characteristics. Now, when we put, let's say, for example, resistance, if we deliberately create a unit of resistance such that we know its value, we know its characteristics, we know its behavior, then in essence, we've created what we call a circuit component, right? So although we don't like resistance generally, we can put a controllable amount of it in our circuit, and this we do by packaging that controlled amount in components. So we call these components electronics or component, and these are things that we specifically what engineer. So there is a component called a resistor. As you can know, or as you can think about, that resistor is probably coming from the word what? Resistance. So although we don't like resistance, we still fabricate known amount of resistances into component called resistors, okay, so that we can use them in circuit, because we know that resistance has the ability to reduce or consume part of the energy that flows in our circuit, right? So in a situation like the analogy I gave, where we have a 9-volt battery and we want to power a 6-volt lamp with, then we would want something that will be capable of consuming that excess of 3 volts, right? So that is how we put certain specific amount of resistances into packages to solve that kind of problems, right? So since we can model that, think about what we can also do for capacitance, right? So then we can actually also model, remember short circuit, right? We said that a short circuit is a short circuit occurs when a circuit or energy source is given a path of least resistance, right? That means it can flow without much opposition, okay? So it happens that even though short circuit is not an ideal event, it's not something that we would like to happen in our circuit, we still engineer some form of resistors to have zero resistance, right? So that we can basically use them as short circuit elements. Okay, so there are resistors with no resistance or zero resistance, and we call them, we use them for purpose of short circuiting points within our circuit. Now, take note. I said that yesterday, I think I mentioned that every material has some amount of resistance, except superconductors, right? So probably you are thinking that, okay, so if we can engineer a resistor with a resistance of 0, does that become a superconductor? The answer is no, okay? The answer is no. It will still have, remember we said that resistance is as a result of the intrinsic resistivity of the materials, external and extrinsic properties like temperature, the shape, the size, and all these things, right? Good. So even though we say that it has zero resistance, this zero is not actually absolute zero, okay? Just that if we even try to round to the nearest 3 decimal place, we will still have 0. But then they still do have some amount of resistance, okay? They are not superconductors, okay? The same way we saw earlier that when we can use this parallel plate to store some amount of energy, right? Now, in component design, we fabricate this concept into components called capacitors to use for this particular purpose, storing electric energy in the form of what? Electric field. Is that okay? So yes, we can fabricate capacitors with known capacitances. Is that okay? So physically, say this component that we are talking about, batteries and all the rest, they have some shapes, some sizes. We can actually deal with them directly in circuit or on paper. Just imagine anytime you want to write or indicate that, hey, this is a capacitor, you have to draw the way a capacitor physically looks like, right? That will be so inconvenient. So we actually have symbols representing all these components, right? Any electronic component that you can think of, there is something called an electronic symbol or a circuit symbol, a symbolic representation of that component, right? So what you are seeing here are the various the circuit representations or circuit symbols for some components that we have there. Okay, so this symbol here is something we call push to break. Okay, so there are some switches that are like that. You push it to rather disconnect. All right, so I just realized that I lost connection. Okay, so let's continue. All right, so like I was explaining, I don't know where you lost me. So let me. So components, we anytime we want to illustrate components, right? We can't draw them. It's that would be a lot of work. So we rather represent components with circuit symbols. Okay, so every component has a unique symbol that is used to identify it, and these are symbols that are internationally recognized, right? Now I should also say that there are two forms of these symbols. There is one set that we usually call the American set, and we have the internationally accepted set, right? Now mostly I use the internationally accepted set, but yeah, if you get if you happen to see those used by America, you should know that yeah, that's also acceptable. Okay, so for instance, there are some switches that by default they connect. Okay, we call them normally closed. Okay, so by default they are connected. When you want to disconnect them, then you push it. Okay, so we call them push to break, and we have what we call push to make. So these are usually what are common, the common ones, the push buttons. Okay, we have a single pole, double throw. So these are all switches. Then we have something called a thermistor, which is a temperature controlled resistor. We have an LDR, light dependent resistor, force sensitive. So all these things here are symbols representing some circuit element or circuit component. Okay, by using these symbols it is easy to illustrate circuits on paper and also talk among people, because assuming I ask Jifa to draw a battery, probably she'll end up drawing something else, right? But with these symbols, it becomes something like a common language among engineers. Okay, so we've talked about resistors so far. This is how we represent a resistor in the international version. Okay, this also is another type of resistor, but here we call it a variable resistor. Then we have also talked about a battery or energy sources. So if it is a single battery, we call it a cell. This is the symbol. And if we have many batteries connected together, many cells connected together, we call it what? A battery. You've probably heard about an LED. That is an LED. So you can use this or you can use that. Okay, this a motor, and there are many of them. Okay, there are many of them. So when we are designing our circuits, we will first design something called schematics, and inside the schematics we'll be using these circuit symbols to represent the various components that we want to use in our circuit. Okay, So when I've been mentioning circuit, right? Now we know what a circuit component is, but what is the circuit itself? Is that okay? So we define a circuit as a closed path that allows electric energy to flow from a source to a load. So if you take this, for instance, we have a battery here which is serving as our source. We have a lamp here which is serving as our load, and then we have what we call a switch which is serving as a means for us to close or open the circuit. That means a means for us to say energy should flow or energy should stop flowing. Is that okay? So this is a typical circuit. So when we say a circuit, it's just the path that energy flows from source to load. Okay. So this circuit element or circuit components, they form the building blocks of circuit. Just like we define atoms as the building blocks of matter and cells are the building blocks of a human body or of an organism, circuit elements, aka circuit components, are the building blocks of circuits. Okay. Now, naturally, we can categorize circuits components into two groups, right? And we can one group we will call sources, the other group we call components. So let me be clear. We can define the elements that form a circuit into two groups. We have sources and components. Okay, so sources are all the elements that have the ability to produce electric energy. Okay, all the circuit elements that are capable of providing the circuit with energy. So typical example would be batteries, right? Then components are all the rest of the circuit element that manipulates or use up this energy. Okay, so it's as simple as that. If you are a source, when you are capable of providing energy, you are a component when you are capable of using, manipulating this energy, right? So that said, let me ask a question. Do you think a capacitor will be a source or a component? Yes. Do you think a capacitor, we saw earlier that capacitors can actually store charges, store energy, right? And at a point it can become the source of energy for the load. So the question I'm asking is, do you think in this scenario, or in this case, we should consider capacitors as sources or as components?
I'd say that I'll classify them as components
Why?
because you've written here that the sources should be able to let the whole circuit function. But I don't think a capacitor can sustain a circuit for it to function like how a source can.
Well, it depends on what kind of circuit. We can actually build up so much capacitors to store so much charges. Have you seen do you know a flashlight?
Yes.
Good. You see, the flashlight, the energy that caused that flash to happen actually comes from capacitor, very huge capacitance, right? So yes,
Okay.
actually, so far as the capacitor has stored charge or stored energy, it should be able to cause something to work, not necessarily sustain it for a longer time, right? But so far that energy can be used to power something.
Okay.
So would you massage your explanation or
Yeah,
your
I
reason?
will still say it's a component because it will first need a source in the first place. Like it has to
Exactly.
first be charged before it can
Exactly.
function. Yeah.
Exactly. So the capacitor by itself does not produce the charge. The capacitor stores the charge. Okay? So if you walk to the well and fetch a bucket of water, you don't call the bucket a well because it contains water. Okay? You don't call the bucket a well. The well is the well. The well is where you got the water from. The bucket is merely storing some of the water that you took from the well. And you see, for a certain amount of demand, you can depend on the water in the bucket by not necessarily going to the well to fetch it. That doesn't make the water a well. The water that doesn't make the bucket a well. It is just functioning as what? A temporary storage for the water. Okay, it's the same thing for capacitors. So capacitors are not sources, they are components. Okay, so let's look at, I think we'll end this session with this. Let's look and take a detailed look at resistors, right? So you join the resistance and you shout ohm, ohm, ohm. Okay, so let's consider a scenario. I like teaching with scenarios. So we have an incandescent lamp that is rated 9 volts and 9 watts, right? So 9 volts means that's the amount of energy it's required, right? The electrons to move, or the amount of, let's just roughly call voltage the energy, because though it is energy per unit charge, it is still the energy, right? So we also know wattage to be a definition of power, right? Or a statement of what? Power, right? And yesterday or in the previous sessions, we saw that power is actually related to voltage and current, or power is actually the product of what? Voltage and current. So our lamp, our incandescent lamp, is rated 9 volts, 9 watts, right? And we intend to use it to light up our garage. However, the battery that we're going to use, or our energy source, is going to be a battery. And this battery, we took it from a scooter, a very small motor, and it is rated 12 volts, 12 amp hour. 12 volts, 12 amp hour. We are supposed to use this to power a lamp that is rated 9 volts, 9 watts. Okay. Now, the question is, how do we design a circuit to make the lamp work? How do we design a circuit to make it? So, first of all, the main challenge this situation or scenario presents is the fact that we have energy mismatch, right? And by energy mismatch, I mean the amount of voltage that our lamp requires is actually less than what the power source is giving us. Okay, that means that the moment we hook this directly, it's going to burn our lamp, and we don't want that to happen. Okay, we don't want that to happen. So the question is, what do we do? Is that okay? What do we do? Now, to solve this problem, we have to find a way of making the battery deliver exactly the amount of energy the lamp requires. Okay, that's what we have to do. Unfortunately, it's not like the lamp has an ear that we can whisper this instruction to for it to behave. The lamp can only do one thing. If the moment it can only supply that energy, it can't do anything less than that, right? So that means that it is up to us, the system engineer or the circuit designer, to make sure this right amount of energy gets to the load. And from the first lecture, that is what we describe as the job of a circuit designer. Okay, so how would we solve this problem? We simply have to control how much current or how much energy flows to the bulb. Okay, so let's go back to the concept that we already know. We know one way, or the one thing that can actually impede the flow of current, and for that matter the flow of energy, is resistance, right? And we also learned just a while ago that we could actually put a fixed amount of a known resistance into components called resistors, right? To do this work for us. So technically, it means that there is a way out to solve this problem. Okay. Now, what this resistance will do, or this resistor will do, is to get rid of that excess energy. Remember, when we take energy from a battery, we can't put it back into the battery. The energy has to be transmitted, dissipated, that is converted to another form, or used up, let me just call it used up, or stored, right? But in this case, the only option that we have is to waste the energy. Okay, only option that we can do, we have to throw that excess energy away, and the only way we can do that is to convert it to heat energy. Okay, convert it to heat energy. So the component that can actually help us do that is what we call a resistor. It's called what? A resistor. So this resistor is going to, when we use it rightly, would help us solve this problem. Okay, so now the question is, how do we do that? Now, resistors come in various forms. So all these things that you are seeing here, they are types of resistors that we have. Okay, so we have resistors that some are fixed. Some they can vary by the technology that we use, by the way they operate, and vary their resistance and all that. Now we shall talk about these things, but right now let's focus on solving our problem. Okay, so the way resistors get rid of this as excess heat, as we want it to do, is by converting it into heat energy. Is that okay? Then the heat energy gets radiated from the body of the resistor. Is that okay? Now, remember in the previous session that we said that the things that affect the resistance of a material, temperature is part. Okay, so look at this. We have a situation where we want to maintain a fixed resistance, and this resistor is doing one job. It is kind of dissipating excess energy, right? And this excess energy is dissipated by converting it to heat energy and then radiating it. That means that this, in the course of its working, it end up affecting itself, right? Because temperature affects resistance, and the resistor has to also dissipate its energy, the excess energy, through heat. Is that okay? So this is something called the Ouroboros situation, right? So there is this snake that when it gets into certain conditions, I think it gets hungry and it begins to feed on itself, right? Just like the resistor is doing. Temperature has the ability to change the resistance, so we don't want that. We want the resistor to stay the value that it was created with, right? But this is the case when the resistor is working, it has to convert that excess electric energy into heat, and that heat, it has to radiate it out of its body. Okay, so it's like the resistor is eating itself. Okay, so I casually call it the Ouroboros situation. Okay, so that is what we happen to have on our hands right now. Is that okay? So let's see what we can do. So this implies that in choosing the resistor, we need to consider not just the resistance, okay, but also the amount of heat that resistor can actually handle. Okay, because if the heat builds up more than the material of the resistor can handle, then that means that resistor is going to burn out. So if you have ever built a circuit and you ended up with your resistors browning out or blacking out or burning out, then it means that you chose a resistor that couldn't handle the amount of energy it was given, okay, or it was dealing with. So yeah, that burning would definitely occur. Now, the ability for a resistor to handle that energy, that excess energy, right, or the heat, is in its power rating. Okay, so when you are buying a resistor, aside the ohm value, you also have to ask for the wattage of the resistor, okay, aka the power rating of that resistor. Okay, so resistors come in various types, shapes, values, technologies, and material compositions. And like I said, all these are various types of resistors, and we use them for different purposes. Is that okay? Each has its own advantage over the other. Now, there are situations where we want so much current to pass, and if you look at the relationship between resistance and current, when resistance, if we want more current to pass, that means resistance has to be very low, right? So it means that for resistors that are used for very high current applications, they need to be bigger by size, because they would be radiating a lot of energy. Is that okay? So there are cases where you would find heat sinks. Now, heat sinks are metals that are connected to components to help it dissipate its heat. Is that okay? So there are situations where these resistors could have so much heat that we will have to attach a heat sink to it to assist in its cooling down. Okay, good. Now, this resistor that you see here, we call it the power resistors or cement type. Usually, if you see big resistors like this, they will have very small value, because the smaller the value, the higher the wattage it has to deal with. Okay, so these kind of resistors that are used for very high current and low resistance, with low resistance, we call them shunt resistors. Usually you see shunt resistors attached to some metallic enclosures or something like that. Okay, because they tend to get very hotter because of the amount of energy they have to dissipate. So for resistors, the larger the wattage, or the larger the amount of energy it has to deal with, the bigger the size is going to be. Is that okay? So you don't just go and say, okay, please, I'm buying resistor at a value of 100 ohm. No, you should also consider how much power that resistor is going to be dealing with. Okay, all right. So we know that the materials that are used for making resistors, like any other physical system, they are not perfect. Okay, so there are some imperfections in resistors. So although per engineering, we would like to be able to create something like exactly 1,000 ohm or 100 ohm, right? We end up with something closer to these values, not necessarily those values. Okay, so it's very difficult getting engineering the precise values because of these imperfections that are found in the materials that are used for making this component, right? So we call something tolerance, right? Aside a resistor having a value and a power rating, there is also a third parameter that you need to consider, which we call the tolerance. Okay, now tolerance gives you information about the deviation from the rated value. So basically, the tolerance is like the error margin of the resistance, right? So if a resistor is rated 1,000 ohms, right, and it has a tolerance of 1%, that means that you should expect an error margin of 1%. So if you calculate 1% of 1,000 ohm, right, that means the resistor can deviate, either increase or decrease by that amount. So it's like plus or minus. Is that okay? Now, so you can actually have the same value resistor, same value wattage, but with different tolerances. Now, usually for some, these tolerances are shown on the resistor as bands, right? So we have brown, 1% tolerance. Usually they are color coded as brown. 2%, 5%, 10%. Is that okay? So I think in Ghana it is common to find 5% tolerance. Is that okay? So these things are important if you are dealing with high precision, or if you are dealing with precision work, like you are building military equipment, you are building hospital equipment, okay, you are dealing with instrumentation and you need a lot of accuracy. Then you cannot be using low tolerance resistance values. You need very high tolerance, and high tolerance means it should have a very low percentage. Is that okay? So this is a good choice. If you don't have it, consider this. If you don't have it, consider that. This is a bad choice. So here it means that the resistance, the value of the resistor is going to deviate for about 10%, right? Now 10% of 1,000 is, I think, 100, right? So that means that in this case, this resistor can deviate by a factor of 100 ohm, and this is actually substantial. Is that okay? So it's not something that you would want to joke about. So when choosing a resistor, three things: you need the value, you need the power rating, and you need to know the tolerance. Okay, now for most cases you may not consider the tolerance, but at least the value and the power rating, these things are important. So now the question is, we know we can use resistors to oppose the flow of current, and in essence reducing how much current is flowing, and that is giving slowing down the energy by way of reducing how much of it is what is flowing. But the question is, as an engineer, how do I choose a resistor? Okay, so to choose a resistor, you first have to know the resistance you need. In fact, it's the resistance that determines what other parameters become. Is that okay? So that's the primary thing you should know, the resistance that you need. Okay, and remember, resistance is measured in ohms. Now the next thing would be that in the circuit that you want to use that resistor, how much energy is it going to drop? How much voltage is it going to drop? How much energy is it going to consume? Okay, so that should give you information for you to know what wattage to select. Okay, then since the voltage translates into power of the resistor required, you can calculate it using the power. We know P equals to what? IV. So once you know the amount of voltage is supposed to deal with, then you can perform calculations to know some other parameters that are important, right? So quickly, I'm going to use an example to explain the things that I've talked about, and I think that will bring us to the end of this particular session. So let's choose for the question that I posed, the garage thing, right? The lamp with 9 volts, 9 watts rating, and we want to power with a 12-volt battery. Okay, so in this case, for the 12-volt battery, what is important about the 12 ampere is that, you see, the 12 ampere is a statement of the energy density of the battery, right? So it will give us information of how long we can actually depend on that battery. And of course, so we have to factor that into how much current we draw from it. Okay, now, but we won't worry about that in the time being. So if we want to draw a very simple circuit to illustrate how we will power that system, that will be it. So we have a battery and we have a lamp, right? And then we would connect a switch here so that we can switch off this battery on and off, right? But you see, the moment we do this, we will have problem. The moment we close this circuit, we are going to have a problem. Okay, so this is actually a switch, something to control or interrupt the flow of energy, right? Now, if we leave this circuit in this way, anytime we close the circuit, the bulb will burn. We will have to replace it, right? Why? Now, since the lamp only needs 9 volts and our battery can source 12 volts, there is an extra 3 volts that we have to get rid of. Is that okay? And we already have said that we can use a resistor for this purpose. Okay, so now the question is, what value of resistance do we need to handle this excess of 3 volts? Okay, so Ohm's law actually comes in handy. So let's quickly look at what Ohm's law is about. Okay, so Ohm's law says that voltage is actually directly proportional to current and resistor. I think we talked about Ohm's law yesterday. So you see, the concept that we treated yesterday, now we are going to see its application. Is that okay? We need to dissipate 3 volts, okay, and its associated energy. So how do we choose the resistance? We need Ohm's law. Now, Ohm's law says V equals to IR. V, we know, would be the voltage that is supposed to be dropped, in this case 3 volts. I is supposed to be the current that we want to pass through the resistor. And once again, remember that sorry, I jumped something. So we have to insert this resistor here, so that the resistor will deal with the excess of the 3 volt after this lamp has taken what it wants. Is that okay? Very, very important. Okay, so we need to know, first of all, we need to know the current that will flow through. Is that okay? Remember, it is the load that determines the current, because the current that should flow depends on what the load requires, right? But then the load was given to us we were just giving voltage and power, no current. But fortunately, we've already learned that we can actually get voltage and current relates to power, right? By the relation, power is equal to voltage times what? Times current. So we know the voltage, which is the wattage, to be 9 watts. We know the power, which is the wattage, to be 9 watts, and we know the voltage to be 9 volts, right? That means that if we make current the subject here, we get I equals to P over V. We slot in the value, and we have 9 watts over 9 volts, which gives us 1 amp, right? So from this, we get to know that we need a current of 1 amp would be flowing through the circuit, or we need to move a current of 1 amp to the load, right? So whatever resistor we are choosing here should be able to allow that 1 amp to flow through it, and in return it should be able to drop exactly this 3 volts. So this is how, or this is what we need to choose our resistor. Great, so let's continue. So from Ohm's law, since now we know the current and we know the voltage, now take note, the voltage that we need is not the voltage of the source. It is the voltage that is to be consumed by the resistor, okay? And that voltage is 3 volts. So you can see it's easy to analyze this things if you consider the voltage instead of all the other stuff, right? We have a source of 12 volt. We want 9 volts at this point. So we just need a resistor that will take care of what? 3 volts. It's that simple. So 3 volts, and it should allow a current of 1 amp to pass. So if we do the calculation, it means that we need a resistor rated 3 ohm. Great. Now we know the value of the resistance. We can walk to the market and get a 3 ohm resistor. Fortunately, a 3 ohm resistor is a standard resistor, something that we can buy off the shelf. Is that okay? But then remember, it is not only the resistance that we need, we also need the power of the resistor, okay? Because you can get a 3 ohm resistor that has a power of half watts, a 3 ohm resistor that has the power of 1/8 watts, a quarter watt, 1 watt, in that order, right? So if you just go to the market and tell the vendor, I need a 3 ohm resistor. Now, those who know their thing would ask you what size, and you would have to tell them, at that point you have to tell them the wattage you need, right? So we usually say something like, oh, quarter watt, half watt, 1/8 watt, 1/16 watt, 1 watt, 3 watt, right? So in this case, when we calculate our power, we said that power is what? Voltage times current. So we are dissipating a voltage of 3 and a current of what? 1 amp. That gives us 3 watt. That means we need a resistor that has a rating of at least 3 watts, right? And that's going to be quite a big resistor, okay? Now, usually it is it is not a good idea to choose the exact value. So let's say after performing our calculation, we know that the resistance, the wattage of the resistor has to be 3 watt. We don't go for exactly 3 watts, okay? What I do, or my rule of thumb, is to double the value for the wattage, okay? So instead of 3 watt, I may go for something like 5 watts or 6 watts. Is that okay? Something more than I have calculated, just to allow room for errors or room for, yeah. Now you see, physically, the bigger the wattage, as we have said, the bigger the resistor. This is because if the resistor is big, it provides it with a larger surface area to radiate the heat, right? So by using a 6 watt or a 5 watt instead of 3 watts as calculated, I rather help my system to stay cooler, okay? Because now it has a much wider surface area to dissipate the heat. Is that okay? Great. So somebody may ask that, okay, now if I choose 6 watt or 5 watt instead of 3 watt, is that not going to affect the parameters of my circuit? Well, the answer is no. Is that okay? So take note that when you double the wattage of a resistor, and here please, I'm being specific, I'm talking about resistor, wattage of resistor. So when we double the wattage of the resistor, it does not change the operating parameters of the circuit. Is that okay? That is to say that if I double the wattage, it doesn't change the resistance. The only thing that gets affected is the size of the resistor, not the resistance of the resistor. Is that okay? So the operating parameters of the circuit will not be changed. Now take note that this is not the same as other components or devices in circuits, okay? The wattage of a resistor is more like related to the amount of heat it can dissipate, okay, or the amount of energy it can dissipate, not about the amount of current it can consume. Is that okay? Exactly. So understand the difference. So it's me increasing the size, the wattage only affect the size. Is that okay? So the only time this would become problematic is in an application where you have space constraint, right? So let's say you are supposed to build a circuit to fit something within a certain space. Then in that case, you have to be very careful about some of these adjustments, because the bigger the wattage, the bigger the size of the resistor, and you may not want that. But aside that, doubling the wattage does not affect the value of the resistance. Is that okay? So take note, okay? So on that note, I would caution that do not calculate the value of resistance. Okay, I won't say do not. Be careful when you are calculating the value of resistance from power. Is that okay? Because like I said, if I end up using 6 watts instead of the 3 watt, my circuit parameters will not be affected, all right. But if later somebody sees my circuit and says, okay, this is a 6 watts resistor, so if it is dropping a voltage of 3 volt, then let me calculate the value of the resistor, you are going to get a wrong value for that. Is that okay? So I advise that when you are dealing with resistors, always try and calculate resistance from voltage, from Ohm's law, instead of from the power relation, right? Unless you accurately know that the value of the power, the wattage that you have been given is exactly as intended and not bloated like as I do. Is that okay? All right. So that is the end for this session. We will end here. In the next sessions, we are going to look at other components. We will specifically look at capacitors. Now, for the rest of the components that we'll be talking about, I'm not going to talk in details about them. It's going to be their circuit functions, right? I'm not going to go into details about those things anymore, right? So I may not even use PowerPoint, or I may, but then I think, yeah. So basically that, okay? We've laid down enough foundation to be able to do something useful. The rest of the foundations, we will talk about them as we get to that point. Okay, so thank you. Let's get into question and answering time.